Okay, so here we go. This is section 2.7, proving segment relationships. So we're going to use those proof skills we did in section 2.6 and 2.5 and built up. And now we're going to use stuff with segments. Basically, the entire section is to work with segments. So we've written two-column algebraic proofs. Now we're going to do this with segment addition and segment congruence. So the first postulate the book actually brings up is something called the ruler postulate. And basically, this just says we can measure the lengths of things. Like for instance, geez, I can't speak. This segment is called segment AB, and for all of us, it's pretty obvious. It's 3 in length, but that's because we see it starts at 0 and goes to 3, and so when we put it from 0 to 3, it means it's 3 in length. If I did another segment, I'll do this as a segment on the computer like this. Yeah, that was the exact same size as this, from 1 to 3, but I instead decided to move it from 1 to, or like 1.5 to 3.5, or sorry, 1/2 to 3.5. It'd still have a length of 3 because I could just say, oh, that's, 3.5 minus 1/2 is 3. So that's all it basically says is, hey, we're going to be able to measure the length of things and use those distances for segments. The next postulate is called the segment addition postulate. And we've already talked about this when we did betweenness. We just didn't give it like a formal name. So the segment addition postulate says if A, B, and C are collinear, then point B is between A and C. And notice this, we talked about this in that biconditional day, that's why I had to bring it up. If and only if. Okay, this happens if and only if, means it's very, very strong. So B is between A and C if and only if AB plus BC equals AC. So I've got a little just 2-second here, a little thing to talk about. Whoops, wrong button. There we go. So segment addition postulate. So hopefully this seems kind of obvious. If I draw on this, what we're saying is the only way that point B can be physically between these two, and that's what we're going to call it, is between these two, is if AB is 7, BC is 2, if AB plus BC equals AC. What that means is then if AB is 7 and BC is 2, 7 plus 2 has to equal whatever the whole length is. So if I know the whole length is 9, this makes sense. Which should make sense, 7 plus 2 is the whole thing, so the whole thing should be 9. The reason we say this is if for some reason, we didn't have the drawing. If I told you that, yeah, B is between A and C, and AC is 10, AB is 2, BC is 7, let's say, we're supposed to add AB and BC together to get AC. Well, 2 plus 7 doesn't equal 10. It equals 9. So there'd be an issue. There's either a gap somewhere, or something's overlapping, whatever it is. So this is just going to say, no, no, no. This is how we know these guys are, these two parts add up to be the whole, basically, or that B is physically between them, as if the two parts add up to be the whole. We're going to use this a lot in class. This is really the big theorem for this section. We use a lot this section. The next theorem we're going to use quite a bit in chapter 4. We'll use the next one quite a bit in chapter 4. Okay. All right, so let's go on here. So in section 2.6, we talked about the fact that we have reflexive property, symmetric property, and transitive. But notice all of these are for equals. The length of AB equals length of AB. If the length of AB equals length of CD, then the length of CD equals length of AB, and so on. Same thing for angles. Well, the question becomes in section 2.7 is, does this work if they're congruent? Okay, so here's what we have to go through and try to prove. Does this work if things are congruent? So here's our proof for you to copy into your notes. So given RS is congruent to TU, we want to show is TU congruent to RS, which that is the symmetric property. So we already know it works if they're equal. What we're going to say is, does it work if they're congruent? And this is the only time we're going to have to do this. So it's going to seem very, very weird and tedious and repetitive, but we have to go through and show this works. We only know it works for equality so far. We don't know if it works if they're congruent. So here's how it works. We have our statements. we have our reasons. First statement is always, well, not always, but 99% of the time for us, the given. Sometimes you can start without it. Okay. That is RS is congruent to TU. Okay. Now, here is where a very important definition we use comes into play. It's the definition of congruent. And that says if they're congruent, they have the same measure. So RS we know equals TU by definition of congruent. And you can just say def of, DEF of, little congruent symbol, we'll know what that means. Okay. Now, step 3, well, I know that if RS equals TU, I can go back and say, hey, flip the order by symmetric property. TU equals RS. And technically I should say by the reflexive property of equality, or just equal. Well, if they're equal, I know they have the same measure. If they have the same measure, they are congruent. By, here's our translator, definition of congruent. Okay. Now, this theorem, even as a math teacher to me, feels like so much ridiculous work for something so simple. And the truth is, yeah, it is. It's ridiculous work for something simple. Here's the point. We'll never have to do this again. Never. Okay? If we know that RS is congruent to TU, we could go through these steps to show that TU is congruent to RS. Or what we have next is a brand new theorem that says reflexive property works for congruence. Symmetric property works for congruence. The transitive property works for congruence. So remember, the reflexive property really is saying anything is congruent to itself. Symmetric property is saying you can switch the order of congruence. If AB is congruent to CD, then you can say CD is congruent to AB. And the transitive property says if AB is congruent to CD and CD is congruent to EF, AB is congruent to EF, or more importantly, if two things, in this case AB and EF, are congruent to the same thing, then they are congruent to each other. And yeah, so they just now work for congruence as well as equality. All right, now the last thing on the video, and in your homework, you've got 3 problems. I'm going to walk you through the first one because this goes back to that segment addition postulate. This is really, really, really important that you get this and are able to set this up. Otherwise, it's going to make a ton of stuff super difficult in class. So it says, I'm going to do, like I said, number 19. Okay, this is the one I'm going to do. The other 3 are yours for homework for tonight on the back of your sheet. So it says, draw a sketch of the 3 collinear points, then write the segment addition postulate for the points. So here's our key. I have to have some sort of segment, because it's a segment addition postulate, with 3 points on it. I don't care where the 3 points necessarily are. They just have to have 3 points on it. And I have to know that E is between D and F, which means D and F must be the outside ones, E must be the inside. Now, what the segment addition postulate states is the only way E can be between these two, oops, wrong way, is if AB plus BC equals AC. So for us, the only way that E can be between DF is if DE plus EF equals DF. There we go. There's our segment addition postulate. SAP. Okay. So your homework is to draw this out for 20, 21, 22 using their letters, and then come up with a statement for segment addition postulate. If you're saying to yourself, this seems way too easy for this homework, for these problems, great. It's supposed to be. If you're saying, this seems really weird and I have no idea what I'm supposed to do, come in. It'll take me all of 5 minutes in the morning to show you before we start class. Okay, thanks. Have a good one.